The Sun is a star about 4.6 billion years old. It is currently in spectral class G2V, so we can call the object a typical yellow dwarf. The surface temperature of the Sun is about 5.780 Kelvin, which corresponds to about 5.510 degrees Celsius. But there are both hotter and colder areas on it. At the same time, the inner layers of the Sun, its outer corona, are heated to millions of degrees. However, the radiation is almost invisible. The average diameter of the Sun is about 1.4 million kilometers and is 109 times the size of our planet. At the same time, the mass of the star reaches 333,000 earthly kilograms, which corresponds to 99.9% of the mass of the entire solar system. We used to think of the Sun as a small star, but in fact it is larger and brighter than 80% of all known luminaries in our galaxy. 92% of the Sun's volume is hydrogen. It is this gas, heated to incredible temperatures, which is the main fuel for the thermonuclear reaction that keeps the vast majority of luminaries burning. As hydrogen nuclei fuse with each other, they release enormous amounts of energy and are converted into helium, which is stored in the center of the star. It currently makes up about 7% of the Sun's volume, or 25% of its total mass. In addition to helium, stellar matter contains other elements, such as carbon, oxygen, nitrogen, and iron. Their relative amounts, however, are insignificant. The Sun consists of several layers of different properties. The central part is occupied by the massive core, the diameter of which reaches 25% of the total size of the star. The temperature of the core is about 14 million Kelvin, and 1 cubic meter of its matter weighs about 150 tons. It is here that thermonuclear reactions take place, which are the source of energy for our star to shine. As a result of these processes, about 4.26 million tons of stellar matter is converted into radiation every second. The nucleus is surrounded by a so-called radiant transfer zone, extending to a boundary of 0.7 solar radius. The density of matter in this region is too high for it to mix freely, transporting heat to the upper layers of the celestial body. Therefore, the energy transfer in this zone occurs due to the fact that the particles of the stellar plasma constantly absorb and re-emit photons. Mathematical modeling shows that the temperature of this part of the star changes from 7 million Kelvin deep inside to 2 million Kelvin at the outer boundary. According to the calculation, a quantum of light generated by the nucleus can spend 10 to 170,000 years in the radiant transfer zone. And only then will it enter the next layer of luminosity. This is called a convective zone, constituting the outermost relatively dense shell of the Sun. The stellar matter here is more rarefied and mobile, so huge eddies constantly arise in the convection zone, carrying the hot plasma from the deeper regions of this layer upward and the slightly cooled outer masses downward. Such convection cells remain stable for 10 to 15 minutes, after which they collapse. After destruction, they create new vortices. This constant motion of matter forms a magnetic field that permeates the entire interior of the solar system. In addition, the Sun is surrounded by an atmosphere consisting of several layers with a complex structure, the lowest of which is called the photosphere. This region emits most of the visible light of the star, so when we look at the Sun we see it. The photosphere is 100 to 400 kilometers thick, and its temperature ranges from 6600 to 4400 Kelvin, or 6430 to 4130 degrees Celsius. Above lies a much more rarefied region about 2000 kilometers thick, called the chromosphere. It can be observed from Earth during a total solar eclipse or with special instruments. It is a very hot zone with temperatures ranging from 4 to 20,000 Kelvin, and its outer limits are permanently covered by spicuous, extended bursts of hot gas from 5 to 10,000 kilometers high. The last region of the solar atmosphere is called the corona. It consists of giant protuberances, flares, and outbursts that can be millions of kilometers in size. The matter that forms the corona is extremely rarefied and incredibly hot. Its average temperature is about 1 to 2 million Kelvin, and its peak temperature can reach 20 million Kelvin. It is this zone that the Parker umbrella periodically crosses, each time plunging deeper into the fiery abyss. If we calculate the energy flux emitted by the photosphere, it is not enough to heat the chromosphere and corona to such high temperatures. This means that there are some unexplored physical phenomena occurring in the Sun that lead to additional heating of the upper regions. There are several scientific hypotheses that attempt to explain this temperature paradox. According to one of them, the chromosphere and corona receive additional energy by dissipating shock magnetic waves. Another assumption is based on the effect of the acceleration of charged particles by the super-strong magnetic field of the star. In order to clarify this question and to investigate the mysterious phenomena observed in the upper atmosphere of the star, the Parker Research Umbrella was created. This automated research station is part of a NASA project called Parker Solar Probe, launched in 2009. After a long 9 years, Parker left our planet for good on August 12, 2018, and headed for the Sun to fulfill its destiny. Before doing do so, however, he had to perform a series of maneuvers to reach his planned orbit. Using Venus's gravity, Parker gradually changed his trajectory, moving step by step closer to the blazing ball of fire at the center of our system. He was ready for the sizzling heat of the star. The probe was designed with a heat-reflecting shield, and all instrumentation was built to withstand the extreme conditions. In addition, Parker's calculated orbit is constructed in such a way that it stays in close proximity to the Sun for a relatively short time, and then recedes, getting an opportunity to release the accumulated heat into outer space. The main task of the apparatus is to determine the structure and dynamics of the magnetic fields in the immediate vicinity of the Sun. In addition, Parker is to measure the energy flux emanating from the Sun, capture parts of the stellar wind, and record wave processes in the solar corona. As a byproduct of the mission, images of Venus and comet Psi 2020 F3 were taken while still approaching our luminary. In order to successfully achieve its goals, the umbrella was equipped with a wide range of measuring instruments: photo cameras, particle traps and magnetic field meters, as well as radiation and radio wave detectors. Many factors hinder the performance of the task. In addition to the critically high temperature, the strongest flow of ionizing radiation interferes with the work of the measuring equipment. In addition, the Sun creates around itself the most powerful noise in the radio band, which means that the transfer of data collected by the probe to the ground also face difficulties. Nevertheless, Parker continues its flight with each revolution of the orbit, stubbornly reducing the distance from the star. At the end of February 2022, it will have to pass through the solar corona again to collect a new portion of data, and by 2024, the distance between the probe and the surface of our star will be reduced to a record 6.5 million kilometers. Calculations show that the probe's energy-reflecting screen could heat up to 1,470 degrees Celsius, which is about 3 times hotter than the Sun's side of Mercury, and only slightly less than the melting point of iron. At the nearest point of orbit to the luminary, the probe already reaches a speed of 163 kilometers per second, and will eventually increase to 200 kilometers per second, making it the fastest space object created by human hands. Unfortunately, the lifetime of the device will not be too long. Having reached the minimum distance of the Sun, Parker will make several turns around it, which will take about a year. All this time it will gradually lose speed, and the instruments on board will be exposed to extreme temperatures and the most powerful radiation. Eventually they will fail, and the probe itself will plunge into the red-hot depths of the Sun, where it will be destroyed by a bottomless ocean of blazing plasma, without a trace. But before this happens, Parker will transmit many valuable data to Earth, thus allowing us to take another step in space exploration, which means his mission was not in vain.